Everyone, I am Pauline Combarnous and I present today the work I did on an observation operator for geostationary lightning image data assimilation in storm-scale numerical weather prediction system. So it is work done in the framework of my PhD with Olivier Comon and Eric Defer at Météo France, and it is following Félix Erdmann's PhD. Now, the motivation of this work is to improve the prediction accuracy of thunderstorms that remain hard to predict in spite of the continuous improvement of numerical weather prediction systems. Now, we know that total lightning is a good indicator of convective activity, and from 2022, total lightning observation from the lightning imager on board the Meteosat Third Generation satellites will be available. So our objective is to assimilate those total lightning data in the French storm-scale regional numerical weather prediction system AROM in France. So to do so, we need synthetic MTGLI data since the satellite had been launched yet. So that work has been done by Félix Erdmann during his PhD. And we also need a lightning observation operator to convert the model variables into a product comparable to the observations. So that's going to be the topic of my talk. So I'll first introduce the data that we used and the method to obtain the observation operator. And then I will present some results and conclusions and the future work that we'd like to do. So as I said before, the Meteosat Third Generation satellite will be launched in the forthcoming years, and it will provide continuous observations over Europe, Africa, the Mediterranean Sea, the Atlantic Ocean, and a small part of South America with a spatial resolution of a few kilometers. So the spatial coverage of the lightning imager is shown on figure A. And it will provide data that are a gridded product of the count of flashes that are passing in a grid cell over a certain accumulation period. So this is illustrated by the figure B, where we can see a flash illuminating the pixels where it passes. And we call this product the flash extend accumulation, or FEA. So now, since these data aren't available yet, Félix Erdmann built a lightning generator with a machine learning algorithm trained with the US National Lightning Detection Network and the geostationary lightning mapper data. So the graph on the right represents the GLM observation, and below this is the product from the generator. So you can see that the correlation is quite good between both. So then this generator is applied to Meteorage network data in France to obtain those synthetic MTGLI observations. So the observation operator is based on the relationship between those synthetic flash extend accumulation observation and one or several proxy calculated from the output of 1 hour AROM France forecasts. So the model has 90 vertical layers, deep convection resolved, and the microphysical scheme IS3. So there is 5 different types of hydrometeors. And we used forecasts from 27 stormy days through the year 2008, so roughly 2 days per month. And the domain of AROM is shown on the figure on the right. Now here is a list of all the proxy that we tested, all encountered in the literature. We can basically regroup them into 2 categories. So first, the microphysics-based proxy. For instance, the first one of the list, the integral of Groppel mass above -5 degrees, introduced by Dirling and Peterson, 2008. And we also have the vertical velocity-based proxy. So for instance, WMAX, introduced by Price and Wind in 1992, which is the maximum vertical speed per column. Now, to relate those proxy with the flash extend accumulation, we split our data set, the 27 stormy days, into a training set of 25 days and a validation set of 2 days. And then the proxy are projected on the flash extend accumulation grid that are pixel of 7 kilometers. And then we apply different machine learning regression algorithm to relate them. So we've tried a linear regression, a linear support vector machine, a multi-layer perceptron, and a random forest algorithm. But it is important to note, though, that the data were processed as a sorted distribution over the whole domain and the whole time period. So they were all regrouped and sorted. It was not a pixel-to-pixel comparison. Now, to evaluate the regression, we use different metrics. So we use the coefficient of determination, R-square, and the mean absolute error. So both formula are reminded on this slide, where FEAM is a flash extent accumulation modeled with machine learning algorithm, and FEAO is the corresponding observed value. And we also use the fraction skill score. So this is introduced by Roberts and Lee in 2008, and it is a neighborhood verification method where the spatial distribution of events is treated probabilistically. So technically, for a given window size, the fraction skill score considers a perfect forecast to be one with the same frequency of events beyond a certain threshold as was observed within the window, regardless of their particular placements. So I have here a simple example of a perfect fraction skill score with an observation grid and its forecast. And they have the same frequency of events, so it will yield a FSS of 1. It is assuming a single window, of course. So typically, the fraction skill score is plotted it is computed for a large range of window sizes, and the score is plotted as a function of those window sizes, as it is shown on this example on the right. So this allows the scale at which the fraction skill score reaches a target scale of 0.5 plus f0/2 to be easily determined. So now I'd like to show you some results. So we have here the the regression we obtained for the validation for each of the 4 regression algorithms that we tested, and for 2 of our proxy. So the 4 graphs on the left are for the Groupel mass, the columnar Groupel mass, and on the right this is for W max. So the white dots are the observation, and the black one are the predictions, modeled FEA. So what we can see is that depending on the proxy, it is not always the same models that perform best. For the Groupel mass, it is the multilayer perceptron and the random forest that have the highest R-square score, higher than 0.97. Whereas the linear regression tend to underevaluate the high value of flash extent accumulation. And for W max, it is the multilayer perceptron and the linear regression that yields the higher regression score. Now here is a table that sums up the performances of each proxy, all the proxies that we tested, again for the validation, and this is only with the random forest algorithm. So the proxy are ordered according to the R-square score. And highlighted in gray are the ones that are based on the microphysics, and in white, the velocity-based proxy. And what you can see is that the microphysics-based proxy are the ones that yield the highest score and the lower mean absolute error. We can also see that when we compare the model flash extent accumulation and the observed one, for a typical forecast hour. So this one is at 19 UTC on the 7th of August 2008. So what we have here are, so the 4 graphs on the left are again for the Groupel mass, and the 4 graphs on the right are for W max. And for both proxy, we have the observed flash extent accumulation, the proxy calculated from AROM, the modeled flash extent accumulation. So for both of them, it's calculated with the random forest algorithm, and the fraction skill score for 2 different thresholds. So what we can notice here is that the flash extent accumulation on the right, modeled from W max, presents isolated structures scattered on the map, whereas the FEA modeled from the Groupel mass has a better spatial coverage that is closer to the observed one. And this is also illustrated by the fraction skill score that is better for the Groupel mass. So a preliminary conclusion of this work So the microphysics-based proxy seemed to perform better than the velocity-based, at least for the training validation partitions that we tested. And we also noticed that for a given proxy, the main difference brought by the different regression models lie in the amplitude of the simulated flash effect and accumulation, but not in their location on the map. And in general, the R-squared score and the mean absolute error are rather good. So we also need this fraction skill score to complete our evaluation. And we would like to investigate the sensitivity to the accumulation period of the FEA. So for everything I've shown before, it was 10 minutes. And we would also like to investigate multivariate regression models and to rank the most explanatory proxy. So that's all for me. Thank you.
Thank you, Pauline. Okay, so here we have one question from Lisa Neef. She's asking, do you have to have only a single proxy? Would it be possible for the FEA to be a function of both scrapple and vertical velocity?
Yes, exactly. So for now, we only test them only one by one to see their influence separately. But we would really like, that's what I was saying in the perspective, to investigate multivariate regression models, so to test several of them in the same time. Because even though the microphysics seems to perform better, we think that for example, having one microphysics-based proxy and one velocity-based proxy, they could complete each other and we could have a better description of our FEA.
I also have a follow-up question, I think, or maybe more like a comment. Have you think about trying like mixing the velocity-based proxy and the microphysics-based proxy, like a linear combination of the two, or some sort of merging?
So that's what we want to try. That's what we are currently working on. So yeah, I'll keep you updated on that. But that's really what we want to try. Yes.
Okay. So if there's more question, then okay, I think there's someone trying to enter. Okay, if not, if you have question, you can always leave your question on the Etherpad, and then Pauline can get to it later on. Thank you again, Pauline, for a very nice presentation.
Yes.